As we learned in the previous lesson, ionic compounds always contain positive ions and negative ions. And what's really important is in a chemical formula, the sum of the charges of the cations must equal the sum of the charges of the anions so that the overall charge, right, that overall charge of the compound is 0. And then, as we've also discussed, the formula of an ionic compound has to be the smallest whole number ratio. So if you're doing, you're putting together an ionic compound and you tell me that the ionic compound is Mg2Cl4, I would mark that wrong because that can reduce to MgCl2. So just make sure you're always doing the lowest whole number ratio. When we are writing formulas from ionic compounds, you're going to write the symbol for the metal Write the symbol for the metal cation first and its charge. It's part of the symbol, followed by the symbol for the non-metal anion and its charge. You're going to use the charges that are on the periodic table. On your periodic table, they are in the upper right corner. And for the anions, you're going to have more than one number in that corner for most of them. So remember that pattern where group 15 is a -3, group 16 is a -2, and group 17 is a -1. And then you're going to just balance the charges, basically. Look for a common multiple. So aluminum is a +3, oxygen's a -2. So common multiple will be 6. So to get to a +6, I need 2 aluminums. To get to a -6, I need 3 oxygens. And so that would be my formula. And you can see that the charges would cancel. So write the formula for the compound formed between potassium and sulfur. So potassium is a +1. Sulfur is a -2. So to balance out the charges, I would need 2 potassiums and 1 sulfur. My total positive charge would be +2. My total negative charge would be -2. When you are naming ionic compounds, the cation name is the same as the element name. So, for example, Na+ is just called sodium. But the anion, we change the ending to "ide." So if I have Cl-, that's not chlorine, that becomes chloride. So the name of the compound, NaCl, you just name the cation, sodium, then name the anion, chloride, so it becomes sodium chloride. Oh, I didn't know it was there. So this is what I just said right there in a table. Cool. So type 1 naming is going to be metals that can only form one charge. Again, if you just look at your periodic table, I'd actually even just disregard this picture here because there are some exceptions, or some, like beryllium, we're just going to always say is a +2. So look at your periodic table, and everything in the first 2 columns, boron, aluminum, gallium, indium, so most things in column 13. And then some of the transition metals only have one charge, and so that's the type of naming we're going to talk about first. So to name those, like I said, you name the cation, name the anion. Bing, bang, boom. So if I wanted to name an Ai, I name the cation, sodium. I name the anion, iodide. Remember, change the ending to "ide." And that's the name of my compound, sodium iodide. Same thing for CaO. Ca is calcium. O is oxide, so my compound is calcium oxide. So when we are naming these compounds here, we're just going to name the cation. So Cs is cesium. F is fluorine, but it's the anion, so it becomes fluoride. Anytime things are in a compound, anytime a metal and a nonmetal are in a compound, they are ions. The reason we don't write the ion charges is because they cancel. or yeah, I guess cancel is the best way to say that, when the ion comes together. So Al is aluminum, Cl is chloride. So we still just name the cation and name the anion. It doesn't matter that there's 3 chlorines. Chemists understand that there will always be 3 chlorines in that formula to balance out the charge of the aluminum. So MgI2 would just be magnesium iodide. And then K3N would be potassium nitride. Okay, just make sure you're changing those endings to "ide." When you are putting the formulas together, as we already talked about, you're going to write out the ion with its charge. So calcium's a +2. Iodide means it's the iodine anion, which is a -1. So to balance out those charges, it would be CaI2. Sodium oxide, sodium's a +1, oxide's a -2. So to balance out those charges, I need 2 sodiums to balance out the oxygen, so it's Na2O. Aluminum is a +3. Nitride is nitrogen, which is a -3. So I have a +3 and a -3. They already balance out, so I would just be AlN. And then strontium is a +2. Phosphide would be a -3. So to balance those out, it would be Sr3P2. So you might have noticed there's something called the crisscross method, and I don't teach it because it can mess you up sometimes, and I'll show you an example of that in a second. But if you just take their charges of the charges, the numerical values, not the positive or negative, of the ions and switch them, most of the time that will lead you to the correct formula. The only time that might be a problem is if you did that with like aluminum nitride, you'd get Al3N3, and as I talked about at the beginning of this lesson, I would mark that wrong because it's not in the most reduced form. So if you do use that crisscross method, just make sure you're always reducing to the lowest whole number ratio. In some of the a lot of the transition metals, there can be more than one charge. So if you look at gold, gold can be a +1 or a +3. And so when I say gold chloride, I don't know if the formula is AuCl or if the formula is AuCl3. When it's something that can only form one charge, like magnesium chloride, magnesium's always a +2, chlorine's always a -1. So it has to always, 1,000,000% of the time, be MgCl2. But for something that can form more than one charge, like gold, if I just said gold chloride, I don't know what the formula is for sure. And so I have to add something to the name to indicate what the charge is. And what you add is a Roman numeral that indicates the charge. So the charge of the metal must be specified in the name, and you do that with a Roman numeral. So AuCl would be gold 1 chloride, because the gold has a charge of +1. AuCl3 would be gold 3 chloride, because the gold has a charge of +3 in that one. So as I just said, when you are naming these, you would put the name of the cation, the charge of the metal in Roman numerals in parentheses, and then the name of the anion. Of course, still changing that to "ide" because that's how we name anions. Oh, so I just went through that on the last slide. Gold 1 chloride, gold 3 chloride. So if I wanted to name CrBr3, I have to figure out the charge of the chromium. And I can do that because the anions always have the same charge. Group 15 is always -3, group 16 is always -2, group 17 is always -1. So I use the charge of the anion to figure out the charge of the chromium. So the total charge I know of the compound will be 0. So I can kind of do this mathematical formula where the charge of the chromium is my unknown. And that would be 3 times the bromine charge because I have 3 bromines, and I know that has to equal 0. So each bromine has a -1 charge, so my total negative charge is 3. So my total positive charge would have to be 3. So the Cr3 plus ion is actually called chromium 3. With these ions that can have more than one charge, their names include their charge. So that's called chromium 3. Br minus we know is bromide. So CrBr3 is chromium 3 bromide. So naming these ones, FeCl2. So again, we're going to start with the fact that we know the charge of chlorine is a -1. I don't know the charge of iron, so I'm going to say it's X. So I know that I have to have basically the X plus the chlorine equal to 0. So the chlorine's -1. There is 2 chlorines. I don't know the charge of the iron, but I do know there is 1 iron in that formula. And then basically you just solve for X. So in this case, X would be 2. And again, this is, actually, let me erase that for a second. So it's always going to be the charge here by how many are in the formula, always. Okay, and then solve for X. So for this one, X equals 2. So we would call this iron 2 chloride. For PbO2, again, don't know the charge of the lead. I know oxygen's a -2. So I'm going to take that charge of oxygen. I'm going to multiply it by how many there are in the formula. I don't know the charge of lead. I'm going to multiply it by how many there are in the formula. And I know when I add those together, it has to be 0. So in this case, X would be 4. So this is going to be lead 4 oxide. And again, I'll say this again, it is always the charge. You're always doing the charge by how many are in the formula. You're always going to multiply those two numbers together. Solve for X, you get your charge of your cation. If you can do that in your head, I don't need to see this work. I'm just writing it out for you so you can see where these numbers are coming from. So naming these, sulfur's a -2. So to cancel that out, we knew iron has to be a +2. So this is going to be iron 2 sulfide. Oops, I don't need a parenthesis there. Don't know why I did that. CuCl, again, copper, -1. So chlorine is -1. So copper has to be +1 to balance that out. So this is copper 1 chloride. And if you wanted to write that out, you totally, just to double check, you can. We get the charge of the chlorine times how many there are. We know that plus the charge of the copper times how many there are would have to be 0. And of course, then X would equal 1. The mercury here, so we don't know mercury. We know oxygen's a -2. So we take the charge of oxygen, multiply it by 1 because there's 1 oxygen in the formula. We take the charge of mercury, which is unknown, multiply it by 2 because there's 2 mercuries in the formula, and we know when we add those together, it has to be equal to 0. So in this case, when we solve for X, we get 1. So this is mercury 1 oxide. And then this last one is going to be tin 4 sulfide. And again, I got the 4 the same way I got all of the other Roman numerals. When you are writing formulas from these names, you do it exactly the same as we did with the other ones, just keeping in mind that that Roman numeral is not necessarily how many, of anything that there are. That Roman numeral is the charge of the metal. So iron 2 iodide means that my iron's a +2. Iodide is a -1. So Fei2. Titanium 3 oxide, that means the charge of my titanium is a +3. Oxygen's a -2. So Ti2O3. Copper 1 chloride, same thing. Write out the charges. I just did the wrong thing. Plus is what that's supposed to be. Cl minus, so it's +1 -1, so CuCl. Tin 4 sulfide. So here's an example of where that crisscross method could get you into trouble. Tin is Sn, +4 charge, sulfur is -2. So if you just did the crisscross, you're going to get Sn2S4, which is wrong. You have to reduce that to SnS2. Last little quick thing is writing these formulas when I have polyatomic ions. Polyatomic ions act just like monatomic ions. So that nitrite ion acts just like any other ion that always has a -1 charge. So I'm back to doing what I've been doing. You name the cation, you name the anion. It just happens, in this case, the cation's name is sodium. The anion's name is nitrite. So NaNO2 is sodium nitrite. So KOH, cation is potassium. Anion is hydroxide. So just potassium hydroxide. Next one, cation is calcium. Anion is nitrate. So just name it. And just like before, we don't have to do anything to indicate there's 2 nitrates. Chemists understand that based on the name calcium nitrate and balancing of charges. So this would be sodium sulfate. And then the last one, NH4, is our only positive polyatomic ion, so that's ammonium. And then PO4 is phosphate. So that would be named ammonium phosphate. When you are writing formulas from the name, you do the same thing that we've been doing. So you write out the cation, you write out the anion. It just so happens that it's a polyatomic anion. Oops. So sodium's a +1, PO4 is a -3, so I need 3 sodiums to balance out the charge of the phosphate, and A3PO4. Next one, copper's a +2, nitrate is a -1, so I need 2 of the entire nitrate ion to balance the copper. So the way I show that is I put it in parentheses with the 2 on the outside. That indicates that I have 2 of the nitrate ions. Aluminum hydroxide, aluminum's +3, hydroxide's -1. And again, I need 3 of the entire hydroxide ions. I have to put it into parentheses because if I didn't put it into parentheses, look at what that's saying. That's saying I have 1 aluminum, 1 oxygen, and 3 hydrogens. That is incorrect because what I have is 1 aluminum and 3 hydroxides. And then lastly, ammonium carbonate. Ammonium's a +1, carbonate's a -2. So I need 2 ammoniums to balance out the charge of carbonate. All right, that is